Hi everybody, Morgan here. So we're going to be catching up now or continuing on with the page 5 of the kinetics outline where we begin to talk about rate laws. Okay? Now, the first thing we need to understand is that a rate law is actually an algebraic equation that you can use to measure the reaction rate. And this is something that's determined experimentally. Okay, so here's a reaction, and this is its rate law. So R is the rate. Okay, K is called the rate constant. And that's a proportionality constant between the rate and the concentrations of the species. So square bracket NO is the molarity of the NO squared, and that number would be determined experimentally. That number is called the order of the reaction. Okay, times the concentration of H2, and that'd be raised to the first. Okay, so that's what a rate law looks like. Now, we can affect reaction rate without actually changing the rate law. We talk about catalysts a lot. Now, what a catalyst does is it changes the activation energy. We also like to say it provides a lower energy pathway. Okay? Now, in your biology class, you probably heard that enzymes are catalysts. But the problem with that statement is it leads you to think that all catalysts are enzymes. That's not true. There are a lot of catalysts that are not enzymes. Even just a piece of metal can be a catalyst. Okay? And you also heard that they speed up reactions. Now that is not a lie, but it's not the whole story. They can also slow reactions down. So we have what we call promoters and inhibitors. Now a promoter speeds it up, where an inhibitor slows it down. And what happens is the promoter lowers the activation energy, but an inhibitor raises the activation energy. Okay? So there are different ways that this can happen. With enzymes in bio, you probably learned about what we call the lock and key method. There are also something called surface catalysts. Now, the lock and key method means that you have a molecule, like an enzyme, there are others, that happen to fit onto another molecule and help orient it properly to react. With a surface catalyst, basically, it gives you a place where the molecules collect, and that helps orient them properly to make them react. Okay? Now, in general, what we say is that you have this energy pathway that we've talked about before, energy and time, and say it looks something like that. What the catalyst can do is the catalyst can provide a lower energy or a higher energy pathway. Doesn't interfere with reactants or products. It just means with the lower energy pathway, more of the molecules have the necessary activation energy, reacts faster. Higher energy pathway, the opposite, goes slower. So we say that these pathways are catalyzed. Okay. Now, a surface catalyst does an interesting thing. First off, absorption, which means you have this nice metal surface here, and it actually collects molecules on it. That's what adsorption is. They move around and get lined up just right, migration, and then they can react. Now, once they've reacted, they basically just leave, escape. okay? And that means they float away. Typically what we might say is that this attraction would be because there's a double bond here, which is a lot of electron density that's negative and attracted to the metal, which is electropositive. Then when the double bond no longer exists, that's when they can float away. This metal weakens it. There's actually a piece of metal like this in the tailpipe of your car. It's called the catalytic converter. It's probably made out of platinum or some type of an alloy of platinum. Okay, that's why people steal tailpipes, because with that platinum in there, it's really expensive. It can be recycled and get a lot of money for it. Don't do crime. Okay, so that's it. That's pages 5 and 6 of the outline. Okay, and then we'll come back again next time to talk about reaction mechanisms. Okay, this is Morgan, signing off.